Okay, can you guys see the screen now? This is the
Yes, sir.
24th lecture.
Yes, sir, visible.
Okay, good, good. So, yeah, just quickly, I'll just go through. We talked about blackout, brownout. We talked about this semi-emergency control and emergency controls. We talked about preventive and corrective control, and then we talked about this flow chart. So quickly want to reiterate few things here. I rushed up last time. So this was the base case, which was A. After corrective action, there will be some situation which will be B. Or and then if there is some issue, then again we will have let's say if there is a contingency C1 which is creating problem here, then we will go to the preventive action, and where we will say that okay, A plus C1 which will give to D, right? And then let's say again we do all the iteration, and then we again come to the corrective rescheduling. We found C2 is another constraint, so you can either write A plus C1 plus C2, or this is equal to D plus C2, or this will give to E, right? So we were discussing this in the last class that A, B, D and E, right? So the cost will be in this sense. Now here just wanted to say that B alone is just the corrective action. So B alone will not be there. It will be actually A plus B, because this corrective A is already there, and on top of that you are making some changes. So for example, let me just make it more realistic for you, that A is basically your day-to-day activity. Basically, if let's say you are earning some money, let's say you are earning 10,000 rupees, or you are getting scholarship of 10,000 rupees, you are distributing that 10,000 rupees for, let's say, buying your clothes, buying some accessories, buying some books, probably paying your home rent, or hostel fees, or tuition fees, or some, you will be distributing that money for that, all these purposes. So that is your day-to-day activity, but that is A. But then we saw, it means just connecting with the logic of COVID, here we saw that initially we took the corrective action where we say that okay, let's buy some medicines and keep it ready with us. But medicines also, people bought this oximeters where you can check your oxygen level. If it is remaining, or it is staying at a particular level, you have to just cross check. If it is crossing that limit, then you have to take some medical help. So those things you have to buy. So those are the corrective actions which you are spending additional in your A. So basically you found out that your initial expense, you have 10,000 rupees, but with all the expenses what you have planned, you got, let's say, 7,000 rupees is your going to be your monthly expense, right? And then by adding this B, probably buying oximeter, you need to keep some medicines at home. So then probably let's say some plus 1,000 is added here. So total it is not 8,000, right? So here it was 7,000, here it is 10,000. Obviously this is higher. And then you saw that okay, no, this is not enough. Probably you need to wear some mask, you need to buy some additional sanitizers, which will come under the preventive action, right? Because just with keeping some medicines and oximeters will not going to safeguard you. So then you need to buy these masks and sanitizers, which will, let's assume it is more plus 1,000. I'm just giving. So total your expenditure is now 9,000, or this will not be 9,000. Sorry, here just wanted to correct here that this plus 1,000 will be from A, or let's say let's just keep it 1,500, because it can be different. So B and D, what I said, it may not be greater than always from B, but it will definitely be greater than A. So probably let's say if I say 1,500, so it will be 8,500 here, right? So just you can visualize, it can be, it will always be greater than 7,000, or the base case value. but it is not necessary that it will be higher than B. So that's one thing which I rushed in the last class because of time. So that's why I just wanted to repeat it here and explain you this thing better. Right, and then probably you can also say, because probably people thought that, I don't know if you know this or not, people thought, okay, traveling by public transport will be risky, coming closer to many people will be risky, so people started buying cars. A lot of people bought cars during this COVID period. So that is the additional constraint what some people added on their life, on their day-to-day activity. And obviously adding car will be even higher. Probably you might have to take loans and additional things, and probably you need to do EMIs, which will eventually lead to 10,000. So basically your expenses are 10, your earning is 10,000. So obviously you cannot expend more than your earning. So you will be eventually be spending your complete 10,000. Maybe 9,000 you can keep, because it depends. I'm just giving a random number. Right. So I hope you got the picture why the cost keeps on increasing as soon as we add this limitations. And similarly, these limitations we are going to see in power system also. As you add contingencies, as you do some corrective actions, there will always be addition of the cost on your day-to-day operational activity of power system. So the base case DC OPF or AC OPF, whatever OPF you take, your base case OPF will be the cheapest cost, and the costs will be added upon as soon as you include the effect of constraints or particular contingency. If you include in that OPF, it will add the cost. Right. So this is what I missed in my previous lecture. So this is just what I wanted to complete here. But you got this idea, right? Any queries? Okay, good. So now let us see. I'm always talking about we can add these contingency in the base case OPF. Obviously, it sounds easy in theoretical sense, but practically how to do it? How to do it mathematically? How to add a contingency in the OPF practically, so, or mathematically. So let us see that in today's lecture. So just wanted to give you a quick background. Everybody knows that base case OPF, let's assume the base case OPF, this is what we have always studied. So we can either use AC OPF, this what we have discussed in our class before the MT, or you can use DC OPF. I can tell you from my experience, people always use DC OPF for their study. They rarely use ACOPF because obviously ACOPF is non-convex and non-linear. It takes even more time to converge. And last time I think Adam or one of you have pointed out that there will be huge number of contingencies which we have to include. Obviously the problem size increases exponentially, and obviously you can imagine ACOPF becomes even more complicated to solve. So let's focus on DCOPF. It will be simple to visualize also, but whatever I'm going to explain, this is same is valid for ACOPF also. So you can means replicate the same logic for ACOPF also. Okay, good. So basically base case OPF is first step is you from the forecasting what we do, we get to know the loads, the value of loads of all the let's say if we talk about, let's say this again, I'm just talking about the same this system here, this load value which I was saying 100 megawatt. This how we get to know. We based on system operator does a load forecasting, and based on this load forecasting he gets the value that okay, somewhere around 100 megawatt this load will be consuming at a particular time interval. So at this snapshot we will try to schedule that what will be the base case generator lines and generators and this load. So the base case OPF is only done for this base case snapshot, so only for the present condition, right, without taking any contingency. We do not consider any contingency. So for example, I can quickly frame the picture in your mind. Is basically I gave this as 2 rupees per megawatt. This generator was 20 rupees per megawatt, and this line was having a capacity of 100 megawatt. This line was having capacity of 50 megawatt. Both generators were having a capacity of 200 megawatt. Now you can obviously tell me the solution here. What will be the solution? Base case OPF solution, and both the line reactances are same. Anyone? What?
Consuming the power from generator 1.
Means with this condition, what will be the solution, optimal solution? You can just say by just thinking, because the reactance
generator 100, generator 100.
Yes, and
generator 2 0.
Generator 2 will be 0. Yes, because I have told that both the line reactances are same, so anyway the power which will be flowing will be 50, although power limit is different, so it doesn't matter, right? So 50 will be the different 50 will be flowing in each of the lines, and 100 will be generated by G1 and 0 by G2. So this is clear, right? Because we always encourage the cheapest generator to generate first. Once it gets exhausted or it reaches its maximum limit, then we move to the next costlier generator. So let's say there was a third generator which was having, let's say, 15 rupees per megawatt. So then once if the first generator was having maximum capacity of 50 megawatt, then obviously we'll cap it at 50, and then that 15 rupees per megawatt generator will generate the third one, considering the line limit violations are not there, right? So this is the base case OPF solution. Now we actually we have not considered anything security here. So basically what we did here is basically we got the base case OPF solution. I'll come to this point, good starting point, after a while, because in optimization you need to give a starting guess. If you have seen this in Fmincon, or even in Newton's first order, Newton's second order, even in this simplex method, we have to give a starting guess to the values, and these starting guess are based on some assumption. Like in simplex algorithm, you took the example or the logic from the coefficients of the objective function. In the Newton's first order and second order, even in interior point method, we actually assumed a random value as the initial guess. So basically, whenever you run the SCO, that is the security constraint optimization problems, you can, because obviously when you include the effect of security here, there will be exponential increase in the constraints, and when it happens, then the problem actually, if you start the problem from random, then it may take longer duration to converge. So better to give a good starting point. So this solution, or the base case solution, can act as a very good starting point for this type of problem, right? So this is just a simple background I was giving here. So this is going to be our optimization problem: F u naught x naught, G u naught x naught, H u naught x naught. Assume that u is the control variables, x is the dependent variables, not represents the base case OPF. So for example, if I have to write the OPF for this, so I'll write 10 pg1 plus 20 pg2 minimization, subject to the equations will be 10 so it will be power balance at bus 1. So anyway, there is no load here, so it will be pg1 equal to delta 1 minus delta 2 by, you can just take the combined equivalent, so it will be, because both the reactances are same, so it will be x by 2. You can take the equivalent of those lines, and pg2 minus 100 will be equal to delta 2 minus delta 1 by x12. And how can we add the inequality constraints? So pg1 and pg2 will be less than equal to 200. Both is actually less than equal to 200. You can add delta, let's say pi and less than equal to minus pi, both deltas, delta 1 and delta 2. You can assume lambda 1 as equal to 0, no problem in that. It is going to not make a difference. Now, in this constraint, we were always saying, because there are two lines and both are having different capacities, right? One is having 100 megawatt and one is 50 megawatt. Can you tell me how to write this inequality constraint for line in a DC OPF? Anybody? Arun, Prasanjit, Papu, Adam. How to write this two lines which are, anyone, just you can try also. There is no harm in trying. You can just give it a random shot. Nivedita, Adyasha. I'm just trying to recall all the names. Anyone? Am I audible?
Yes, sir, you are audible.
Yeah, Ali, you can, if you want, you can help me with writing this equation.
Actually, no idea about
So delta 1 minus delta 2 by x12 should be this.
This will be by 2. Yes, exactly. So you have to ensure delta 1 minus delta 2 by x12. Let's say dash, or both is going to be same, so no dash. Yeah, both is same. So this will be less than equal to, or upper by less than equal to and greater than equal to. What will be the value?
-50 and 0.
Minus 50, right? Because power can flow in the reverse direction.
Minus.
Right.
Yes.
Will there be just one equation? Because there are two lines. Will there be another equation?
So two equation for 100 also, minus 100 to 100.
So can you tell me the equation here?
Delta 1 minus delta 2 divided by that x 1 to that.
Yeah, because the
another.
reactances are same.
Ah,
Right. So do you agree with these two equations? Everyone?
No, sir, because delta 1 minus delta 2 by x12, that will be a same value. So how can we restrict it to both the equations? Like in one we are telling to be less than 100, one should be less than 50. So
Okay. Good thought process. Nice. Anyone else also want to give their opinion? Do we need to write two equations here, or do we need to write just one equation? This is the question. Nivedita
sir,
says that.
equation,
Please, batao.
so one equation and it should be 50 because that is the lower maximum limit. If we keep 100, then line 2 limit will be violated. But if we keep 50, then line 1 will have no objection.
Agreed. Means, yeah, I got your answer. Anyone else want to try here? Anyone else want to try? I'm not, actually, I just do not want to disclose the answer. That's why. Anyone else? Adam, Ali, Adyasha, Arun. Are you guys here? Let me see who all are here. Oh, acha, okay. Pushpendra is here. Okay, many people did not join today. Okay, ठीक है. So Pushpendra. Okay, chalo.
Yes, sir.
Yes, please, Pushpendra. What do you think? What should be the situation here? Means my question is, did you hear my question? Pushpendra, can you hear me? Okay, I think I lost him. Okay, Adam, do you want to try?
So the question that is
Because there are two lines, and do we have to write two different equations for these line limits, or just one equation? Nivedita said that we just need one equation with less than equal to 50 and greater than equal to minus 50. What is your comment here?
Sir, we can put one equation minus 150 to plus 150.
Okay, okay.
Some summation of capacity for two line.
Okay. But do you
so
think,
it
yeah,
is,
please.
I think the maximum limit is here is 100 or 200 you mentioned.
No, it's 100. One line is having
It's
capacity
100.
of 100 and
So
one line is
after we
50.
divide it by x12, it will be yeah, it is 50. So perhaps it should be one equation.
Which one? 51 or 101?
Yeah, 51.
Okay, 51. Okay, so you and Nivedita agrees on 50. Ali said we can add it. Okay, ठीक है. So just wanted to get back to Ali first. Ali, if we add and make it 150, so power flow, because this delta 1 and delta 2 can take a value which can lead to this line. In the second line, the power flow may lead to more than 50, right? Can you see this?
Yes.
So that will not be the case. What Nivedita and Adam said, that is partially correct, because for this system, yes, we can just write this equation. You do not need to write the minus 100 plus 100, because whichever is giving you the minimum limit, because the reactances are same. That is why we can add this equation here. So please make a note here that because the reactances are same, that's why we can add just one equation and it will solve the problem. But if obviously practically there is very less chance that reactances are going to be same, it is going to be different. So if the reactances are different, then you need to write two different equations. Right? Agreed? Nivedita, Adam?
Yeah, it's clear, sir.
Good. Yeah. So it will, if the reactances are same, you can just take the minimum, the line which is having the lowest limit, you can add that, and that will solve the problem. But if the reactances are different, you need to add equations for each line, right? So just remember this. Okay, good. So with this, we will be able to solve this problem. So these equations over here, the equality equation, this G is this two equations. The inequality equations are all the inequality equations what I wrote, and then the objective function is this one, 10 pg1 plus 20 pg2. Right. So this will give you this solution what everybody said here, that 100 will be generated by pg1, 0 will be generated by pg2. This is going to be your base case OPF solution. Right. So assume that there is no x naught, because there is no, or probably you can say u naught as pgs and x naught as deltas. Probably you can say this because we say the same logic for ACOPF. So you can say this x naught is delta and u naught is pg, right, for this case. So this is the base case OPF solution. Right. And here I'm assuming that the objective function and constraints depend on the time scale of the problem, because here I'm writing the problem only for one timestamp, or let's say one time window, which can be for 15 minutes or an hour, just one time window, not the complete time intervals. And also this problem can be solved only for the day ahead or real time, so it depends on the whatever is the operating practice of the regulator. So this will come later on, but just to for your understanding, let's assume we are running this in a day ahead. So for tomorrow, because system operator does not know what is the load going to be on tomorrow at a particular time interval, so let's say he forecasts some load for this system. Let's say he forecasts that tomorrow at this time interval it is going to be 100 megawatt of load. Then today he is planning of this security constraint that, okay, if this line gets out or if this generator gets out, how am I going to ensure that the system is, because we will do this security analysis. The next step after, once we get the base case OPF, the next step was to do a security analysis. In that security analysis, you will find some are critical contingencies, some are non-critical contingencies. In our case, we told that if the in it means, I'm just taking again the problem what I gave in MTE, is that I mentioned that there is sufficient ramping capabilities of both the generators, right? So if I'm saying that both the generators have sufficient ramping capability, that means the corrective rescheduling was enough, right? You did that, solve that problem, and we gave the answer in the MTE that, okay, we can just reschedule the generators and immediately balance the load, so we do not have to worry about. So basically what we will do here, that from the security or the critical contingencies, so it was G1, L1, L2, G2, right? So I'm not repeating everything here, you know the values and data here. So we knew that if L1 is going to get faulted or outage at L1 or at G1, these two contingencies will force the system to change, right? Do you remember this? So L1 and G1 can force the system to change. So basically, if we do the security analysis, it will give you the solution that L1 and G1 are the critical contingencies, L2 and G2 are the non-critical contingencies, right? We discussed this in the last class. So now we know L1 and G1 are the critical contingencies. Now, based on this critical contingency, we will go to the corrective rescheduling step. Right. So in the corrective rescheduling step, what we will do is basically we will see that if, let's say, L1 goes out, then what we have to do, we have to again, I think I'll have the optimizations considered the base case. Yeah, here what we have to do. So when we go to the corrective rescheduling problem, this is what this optimization problem we have to run to get the optimal solution. This here, it is easy to see what will be happening. So let's say if L1 is out, right? Let's focus on this. L1 is out. Now in this corrective rescheduling, what you will do, the objective function is going to be the same, which is minimize 10 pg1 plus 20 pg2, right? Subject to, you will write again same equation, pg1 minus pg2 by delta 1 minus delta 2 x12 by 2, p2 minus 100 equal to delta 2 minus delta 1 by x12 by 2. This is by 2 I'm writing because I'm equivalenting both the lines, and obviously if the reactances are different, then you cannot do this. You have to write two separate equations, right? And then there is P1, P2, both will be less than equal to 200 greater than equal to 0. Delta will be pi and greater than equal to minus pi. Now here I am mentioning L1 is out. Then what is the solution going to be? What change I have to do? So one thing, I made a mistake here because L1 is out. This will not be here, right? Because there's just one line which is L2. So you have to write just x12, x12 because L1 is out. Now, if L2 is there, then this is very simple, that delta 1 minus delta 2 by x12 should be less than equal to 50, and this will be less than equal to 50. Right? So basically, now you can see that in the previous base case OPF, you were getting the solution where G1 was 100 and G2 was 0. Here you will see, because L1 is out, here you will see that G1 will generate 50 and G2 will generate 50. Right? Now, what we did here is basically this problem is, what we did is basically we knew that, assume that a particular contingency is taken place, which is L1, and then we are rerunning the optimization problem to, after excluding that contingency or excluding that line or excluding that generator, we'll run this optimization problem to see that everything is satisfied or not. Right? If both if lines is out, and if, let's say, you saw that the solutions of this PG1 and PG2 are going to change, so that means the base case was obviously not able to handle this critical contingency. So in the corrective action, you need to change G1 to 50 and G2 to 50. Right? Here, a caution here is that I mentioned that the generators are having sufficient ramping capabilities, but obviously in practical situations you cannot have infinite ramping capabilities. Obviously generators are mechanical machines, they cannot ramp up that fast, especially if it is nuclear generators. Even the coal-based generators, they are very limited by their raw material or the source by which it can change. So therefore it is very, very limited on ramping. Hydro, on the other hand, hydro, diesel, gas, they are very fast ramping generators. Right? It's for obvious reasons. Obviously you can immediately change the turbine speed, and then you can generate more power. Right? This condition, what sufficient ramping, I have not included here. Let us add that, and that's what I was saying here is basically once what you will do here, that you will run the base case optimization, but you will run that base case optimization removing the limit violation or removing that contingency what you have you were observing. So let's assume I was studying for L1 when L1 was out, because corrective rescheduling is basically we are preparing a lookup table. So when L1 is out, we will run the same optimization problem, and here this equation, so this is fine, this is the kth contingency. So our line outage of L1 is actually kth contingency. So there can be 4 outages in this small system. G1 can be out, G2 can be out, L1 can be out, or L2 can be out. So all these 4 can be there, and obviously we are just considering one outage at a time. We are not considering all the outages at a time, obviously. So for this kth contingency, I'm writing this optimization problem, and here what we will do is add this last constraint. So this is common, f uk xk, because you are deriving this value of pg1 and pg2 once the contingency has taken place. You are writing the power balance equation once the contingency has taken place. So that's why I mentioned here x12, not x12 by 2, because obviously we have assumed that the contingency has taken place. You have written all the inequality equations assuming that the contingency has taken place. So obviously this makes the problem without the contingency, or in excluding that line or generator which is assumed to be having contingency. Here this you have to add additionally, and what this equation is basically PG minus PG L1 I can write, and PG naught. This can let's assume if we talk about the first generator, let's say here if I write 100 and here I write minus 100. What this means is that a generator, PG1 generator, which was initially generating at 100 megawatt, this generator can ramp up to 100 megawatt and ramp down to 100 megawatt or till more 100 megawatt. So basically the change, because it was having a capacity from 0 to 200, so obviously it can go maximum till 200 or minimum can 0. So obviously I'm assuming that when I'm saying that infinite ramping capability, that generator can immediately ramp up to 100 more 100. So basically the difference is 100. So basically it can go till 200 or it can go till 0 immediately, right? So this is 100 and plus minus 100. So can you tell me, adding this equation, will the solution be same or will it be different? What will be the solution in this case, in this optimization problem? What will be the solution? We said that in the optimization problem, when we assume that there is infinite ramping capability, PG1 will be generating 50, PG2 will be generating 50. My question is, after adding this constraint, this PG1, PGL1, this one, will the solution remain same or will the solution will be different? Anyone?
It will be the same because the value of BG1 and BG2 are same also. Or all of them are below 100 megawatt.
Yes, because the line, this is going to be variable here. So this is actually PG L1 when L1 has taken place. Here also L1, here also L1, and K is also here also L1, L1, L1. So for that L1 contingency, we are trying to find all the values, right? And PG1 naught is nothing but 100, right? So obviously we are giving the generator full freedom. He can generate till 200 because 200 minus 100 will be less than equal to 100, or minus 100 where 0 minus 100 will be minus 100. So we are giving full freedom to the generator, right? So that's why the solution is going to be the same, and that's why I wrote in that question that assume that the generators are having infinite ramping capabilities. Now let me quickly change this here, this last constraint, and with this I can end this class. Let's assume this is minus 10 and plus 10 just for PG1. I'm not adding for PG2. Let's assume that PG2, or I can add this also here, PG2 L1 minus PG2 naught will be less than equal to 100, less than equal to minus 100, right? So now what the solution is going to be? I have changed the solution from 0, sorry, it was initially for the generator 1, because let's assume it's a nuclear generator, and nuclear generator do not have sufficient ramping capabilities. So and let's assume PG2 is a diesel generator, so PG2 can still generate and reduce maximum at plus minus 100, but PG1 can only change by just plus minus 10 megawatt and not more than that. So what will be the optimal solution now? Quickly, what will be the optimal solution? Can you guess? What will be the value of PG1 and PG2 when L1 is out?
BG1 should be 10 and BG2 90.
No, PG1 initially it is 100. So when I'm adding this here, this equation, let me just change the color here. So in this equation, here I'm adding plus minus 10. Initially it was 100. So maximum it can go till 110 or minimum it can go till 90. It cannot change beyond that. It is the difference I'm talking about. Initially, it was already generating at 100 megawatt. From that, because base case is already there, he is generating currently at 100 megawatt in the system. Now you are assuming if that line gets out, what change you have to do in the system?
So we have to shut down the generator 1 and whole load will be in by generator 2 because 90 if minimum that can be done, generator 1 is 90 and
Yes.
line 1 is already out.
Yes. So what will happen if it generates 90?
So line 2 will be overloaded and it will.
Good. Yes, exactly. So because it was Pushpendra, right? Or Prasanjit?
Yeah, Prasenjit, sir.
Okay, Prasanjit. Okay, good. Yeah, I was just yeah, because I'm just listening to your voice and trying to recognize your name. Okay, ठीक है. So basically, you are right. Yes. So L1 is out. So if the generator 1 it generates, it has just the freedom of plus minus 10. So initially it was generating at 100 megawatt and now he has a freedom of just generating plus minus 10 megawatt. So obviously he has to reduce. So maximum what he can reduce till 90. He cannot reduce beyond that. And even if he generates 90, the power flow on line 2 will be 90 megawatt and line 2 can only support 50 megawatt. We knew from our data. So basically the G2 cannot provide 90 even and it has to shut down and then PG2 will be taking care of the complete load balance. Right, but just wanted to give you a caution here. Prasenjit was not 100% right. It was partially right because I have not added any constraint or any equation to switch off the generator. And practically you cannot do that. You cannot tell a generator which is generating 100 megawatt to immediately shut down. And especially for nuclear or thermal generators, you cannot do that. It is against the rules, and we are going to see this logic when we see the unit commitment. There we will see how to switch on the generator and how to switch off the generator for power system operation. Right. So yeah,
sir, for the case that I mentioned it, BG1 should not generate only 10 megawatt and that remain 90 megawatt should be generated through BG2?
No, because of this limitation, because this 100 is there. So this equation looks like this. If I'll write it in number sense, it looks like this. So obviously it cannot come to 10. If it comes to 10, then it will be 10 minus 100 will be minus 90. Obviously it cannot go till minus 90. It is limited by just minus 10. Do you see this, Adam?
Yeah. This is a question that I.
Yeah. So you cannot do that. You cannot do that. So there's only option to shut down the generator. But obviously this is also not there in corrective rescheduling. Again, I'm not supporting that. Prasenjit was partially correct. In corrective rescheduling, you cannot switch off the generator. Generator will remain, and then you have to take a decision. So this is an issue. Now from here, if let's say I keep plus minus 50, then obviously you can see that it can reduce to 50 and PG2 can generate 50. Right. So basically here what are we doing? This last equation here, this is adding the practical conditions. Obviously in practice generators cannot ramp up and ramp down immediately, so this practical condition is added by this equation, and this equation ensures that the generator will be able to reschedule or not. Right, and then based on this you will prepare the lookup table. So if it is plus minus 10, then there is no option practically in corrective rescheduling, because I have excluded the option of shutting down the generators, so then only solution is to basically forcefully shut down this generator. There is no option, you have to forcefully shut down the generator, and you have to or no, so sorry, you cannot do anything in corrective rescheduling. Now you have to go into the preventive action, right? Because I am excluding the option of shutdowning the generator here, you have to go for preventive rescheduling. There is no other option, because this, when I say plus minus 10, because when it was plus minus 100 or plus minus 50, we were able to balance it and satisfy in corrective rescheduling. As soon as I say it is plus minus 10, then we see that this equation cannot be satisfied in corrective rescheduling, and that means you have to include this contingency L1 into the preventive action, because you know now you know that this contingency, you cannot rectify the system in the corrective rescheduling if it is plus minus 10 megawatt. Do you see this? That we are not able to satisfy this. What will happen? It will eventually we have to force the system to blackout or load shedding. It is similar to in COVID, people were dying, so we have to take some preventive action then. So that's what is happening here, because system will die out, because we cannot run the generator. We have to forcefully desynchronize the generator and shut down the generator. There is no other option. So therefore, obviously, we will not do that thing. So we have to save the system from dying, right? So that's the motive. We have to save the system from dying, load shedding, and therefore we have to include this type of contingency in our preventive action plan or preventive control action plan. You get the difference here, what I'm saying corrective rescheduling and what I'm telling about preventive rescheduling. Right. So with this, I'll end the class today. I thought I'll complete this because I have already taken my time. Let me just continue in the next class from here.